Okay, should I start or do you want to wait another 2 minutes?
Yeah, I guess you can start.
Okay, so let me sort of review what we've been doing so far. We've been considering problems with small noise or weak noise, depending on what you want to call it, and the specific type of equations that we were looking at, which were in one dimension, took the form of x dot equals to v of x plus square root of 2 of gamma of x over n times eta of t, where this is Gaussian noise, Gaussian white noise. And I want to stress that the model can be in or out of equilibrium. Okay, so the equations that we write, you don't have to have fluctuation dissipation. This V could be a bias driving you in one direction around the ring. And I might give you I might discuss a problem like this later today. Because it's useful, I'm going to write the generalization for general D. I'm not going to use it a lot, but I'm going to give a small homework problem with it. So the generalization to general dimensions, which you can build on to do also field theories, if we discuss them today, then that's essentially what you use as an infinite dimensional vector. So we have, again, a deterministic driving term, and then we have a noise term, which I'm going to denote as a matrix, which again can depend on the vector x times another noise term. And you can, and again, I'm going to assume in what I derive Gaussian white noise. And the G matrix is going to be proportional to 1 over square root of n. And in fact, it doesn't have to be even a diagonal matrix, because you could have eta acting on some degrees of freedom, etc. But okay, I won't get into it because we're not going to use it. Okay, with this equation, we developed a host of techniques to calculate the large deviation function. Namely, we were interested in calculating the probability of some configuration. And I just remind you that there's a host of other large deviation, like averages of quantities, which you can calculate, and that's a mixture of these techniques with the one I was describing in the first lecture. And we focused on here on path integral methods, and specifically we derived the Lagrangian form of the action, which in one dimension takes the form of n, the integral from 0 to t of dt prime of this guy. Okay, and I'm just going to write the generalization to general D so that you have it. So it's n, it looks very, very similar, except that of course we have matrices everywhere. So it's x dot minus v of x, and then we have a matrix gamma inverse. And again, I'm not going to derive it. I leave it as a small exercise for you guys. It's not very hard. And gamma is equal to 1/2 of G transpose. Okay? So this was the Lagrangian form. There was an equivalent Hamiltonian form that you could derive using a Martin-Seja false formalism or by a Legendre transform. And in that case, the action in one dimension takes the form of n 0 to t dt prime of x hat x dot minus a Hamiltonian. And the form of the Hamiltonian was x hat v of x plus gamma of x times x hat square. And I stress that it's proportional to x hat. And the reason to understand why everything here is proportional to x hat, because it really came from this Fourier transform. And x hat was the momentum and it's multiplying the whole delta function, which is the equations of motion. So everything by construction has to be proportional to x hat. And in general dimensions, in general dimensions, I'm going to write this again. It looks very, very similar. We have x hat dot x vector now minus a Hamiltonian, which is a function of this momenta and position, and the Hamiltonian should really be a function, is given by x hat dot v of x plus x hat dot gamma and x hat. And again, it's proportional to x hat. And the idea was that because we have this n in front, if we're interested only in the leading order behavior in n, then what we can do is just minimize the action. Okay, so what we did was, I'm just repeating what we did to calculate the steady state. What we do is minimize action. And this gives us most probable history. And we plug that in action, plug in the action, and then we obtain the large deviation function. So the procedure is straightforward. I mean, technically it can be very challenging, but it's straightforward. And again, when I say minimize the action, what you do is you find a trajectory, and that means that in the Lagrangian, I find x as a function of t, and in the Hamiltonian, I find x and x hat as a function of t. Okay, so that was the procedure. And the next thing I argued was that in the steady state, there's a simplification that occurs, and it's that the Hamiltonian along all the solutions, which corresponds to the steady state, and the steady state, I remind you, I start at t at equals to minus infinity, and I evolve the system up to time t equals 0. We did it from 0 to tf and sent tf to infinity. It doesn't really matter. And I argued that for solutions which satisfy this, the Hamiltonian is 0 along the action. And I had some email correspondence yesterday, so I want to go a bit slower about this point. So one way to think about it was the one that I was trying to say yesterday, was that because the trajectory takes an infinite amount of time, what happens is that the only solutions that can satisfy this, only solutions are ones which start at fixed points of dynamics. Okay? And I remind you that fixed points of the dynamics are ones which have no noise by definition. Okay? So the only fixed points that we can have are ones which we put the system without any noise, meaning I remind you that x hat was identified up to a constant as being proportional to the most probable realization of the noise. So the only fixed points that can occur are where x hat is equal to 0. And because the Hamiltonian is equal to x hat times something, this implies that since the trajectory spent started at the fixed point, that implies that H is equal to 0. Now, I want to argue for this in a slightly different way, because I started doing it yesterday and I did it in a very sloppy way at the end of the in the end of the talk. So I want to understand this again. So I think there was some confusion by people thinking that this H has something to do with the actual energy of the system. I remind you, this is just a general Langevin equation. It doesn't have to have anything to do with energy in it. And what I want to argue is that this H is actually related to eigenvalues of the Markov matrix. And specifically, H equal to 0 is associated with the 0 eigenvalue of the Markov matrix. So to do this, what I'm going to do is I'm going to write down the Fokker-Planck equation. I'll skip a bit of math, but just a bit, plus 1 over n, the second derivative of gamma times p. So this is our Fokker-Planck equation. And what I'm going to do, I'm going to analyze it using a standard WKB procedure where I guess a solution where the probability distribution takes the form of e to the minus n phi of x, and I'm going to be interested in the steady state. So equal to 0 is steady state. That's what I mean here. And when you do this and you keep the leading order in n, and I leave it as a small exercise, you find this expression. Okay? And now I remind you that the Hamiltonian took the form of x hat v of x plus x hat gamma x hat. So what this equation that we have here is just what we know from analytical mechanics as the Hamilton-Jacobi equation. And where this is the momenta at the end of the path. And this equation tells us that the Hamiltonian is 0. And if it's 0 at the end of the path, then it's 0 also because the so-called Hamiltonian is conserved through the dynamics, then it's 0 throughout the whole process. Okay, so questions about this? Somebody doesn't remember Hamilton-Jacobi, never liked it, wants a refresh?
Hi, Yariv.
Yeah.
Hello. A very quick question. Actually, it's if you could go back to the first line you wrote, the first page.
The first page. Yes.
Yeah, first page. When you wrote down the Langevin equation. So even in the multidimensional case, you consider like a colored noise with some correlations, right? You put in front of the noise some dependence on the space.
On the space, but it doesn't mean that it's colored. By colored, what I mean at least is that, so what I assume here, that eta of I, eta of j, of t prime, for example, is at least proportional to delta of t minus t prime. So it doesn't decay with, say, an exponential. There's no, so that's what I mean by white noise and not colored noise. It can be but multiplicative.
Yeah.
Also in these.
Sorry. Yeah. That's what I meant. Sorry.
Okay, and that doesn't change anything here, actually.
Not even. I understand that in the one-dimensional case, it's always possible to like change the variable and make the multiplicative noise and an additive one, changing basically the potential. But in the multidimensional, in the d-dimensional case, I mean, I don't know if this is possible, and if not, how would the Lagrangian form change because of this?
Because of the colored noise. So there's So I'm not going to pull this off the top of my head, but there's actually there's a way of doing it, which was done by, if I remember correctly, I haven't done it here, but it was done by Alan Bray, and I hope I'm spelling his name correctly, and Alan McCain, and I think the years are about 90s, so you could look it up. Okay.
Thank you very much.
Yeah, there's a Lagrangian way of doing that if you can't do this addition of an extra variable.
Okay, thank you very much.
Okay, other questions?
Hi, Yariv, in the same same expression.
Same.
If gx is equal to 0 for some choices of x, then would the same thing go?
Yeah.
Through?
No problem. A classical example is that when you have a density of particles in the system, then there's no particles, there's no noise.
Okay.
So this is a standard choice actually when this happens.
Okay.
Okay, other questions? Okay, yet another way.
There is a question in the chat box.
Sorry?
There is a question in the chat box.
Okay, how do you fix the initial conditions? So remember, we're solving a problem where we start at t equals to minus infinity at the most probable state, and we end up at t equals 0 at the x that we're interested in. So in the Hamiltonian version, we have two first-order differential equations in time. We have two boundary conditions, so that fixes x hat. Okay?
So, Yariv, so the key point is that because it's an infinite time, so you need to start from a fixed point, and then that sets that x hat to 0.
Yes, that's the first way of thinking about it. The second I try to show using the Hamilton-Jacobi, and I want to show a third one just for fun.
Okay.
So the third method is to look at the action in the Lagrangian form. And the Lagrangian, I'll do it quickly because I hopefully convinced you of this. So in the Lagrangian form, this is the action. Now, if you remember, this is just the noise up to a gamma, right? And the noise in the most probable history is related to x hat. So actually, when you do all this math correctly and you replace the action with the value of the noise, you find out that the action takes the form of the x hat gamma x hat. And that means that unless x hat is 0 for almost all the trajectory, then you're accumulating an infinite amount of action, and that by no means can be a minimizer of the action. Okay, so all these things are different ways of saying exactly the same thing. That the Hamiltonian along the trajectory is 0, and that implies at the end of the day that when we calculate the large deviation function in the Hamiltonian formalism, all we have to do is just do this integral. Okay? And at the end of the lectures yesterday, I did two things. I discussed first the case, so ended with case with single fixed point. And then things were simple enough. We have, say, the oscillator, we have the fixed point, we started the most probable state, and then we just look for a trajectory that shoots us up into the position that we're interested in. And then I looked at cases where you have metastable states, and the procedure was somehow more involved. We had to first evaluate the value of the large deviation at these fixed points. So this was x2, this is x3, and phi of x1. And after we calculated these guys, using the transition probability between them, we could calculate the value of the large deviation function everywhere. A final comment is that one of the recurring themes was that we observed, I haven't proved it, and I don't think I'll prove it because I don't have enough time. It's not very complicated. If you go to the literature, you can find it there. What was a recurring theme was that we looked at the system in equilibrium. What we saw was that trajectory uphill, which is what we called for creating a fluctuation, was the time reversed version of the downhill trajectory. And this was just a manifestation of time reversal symmetry that's inherent for equilibrium problems. So that means that if we solve this relaxation problem in the equilibrium problem, so this is down, then we get the uphill for free, and the uphill is just the time reverse of this guy. So that makes equilibrium problems very, very easy in terms of the calculation. You don't have to worry about all these complicated uphill dynamics. Now, out of equilibrium, this breaks down. As you might imagine, out of equilibrium, uphill is very different from downhill. Just two different trajectories. And what I want to do is, because I'm not going to analyze it here, I want to give you, for those of you who are motivated enough, I want to give you a sort of silly homework, but I think it's fun to explore, and it's not too hard to solve using the methods that we discussed. The expressions are a bit long, but if you use Mathematica, it's not a big deal. So what I'm going to do is I'm going to take two oscillators. So two particles, which are sitting each in its own spring. So there's a position of particle here, x1 and x2. And then I'm going to connect them with a spring constant k, which, just to simplify things, is the same as a spring constant in each of these oscillators. And what I'm going to do is that I'm going to couple these baths to temperatures T2 and temperatures T1, which in general can be different. And I'm going to write down the equations of motion, and it's sort of a fun exercise to solve both the relaxational dynamics of this and how fluctuations are created, and convince yourself that there's really energy flow from the hot bath to the cold bath. And I think once you solve this, you'll see that it sort of pops out of the dynamics why in this system energy has to flow from the hot bath to the cold bath. And you'll see that it's the real reason is that it's much easier to create a fluctuation in the hot bath, and that actually drags the the particle connected to the cold bath with it throughout the dynamics. So let me just write down the equations of motion. So it's minus mu kx1 plus mu k. So this is the coupling, and then I connect it to a bath. So there's sigma 1, 1, and there's a noise here. There's another oscillator whose equations of motion are given by just an almost identical version of this, but now with the different amplitude of the noise. And we assume that the average of eta I is 0, and the average of eta I of t, eta j of t prime, is equal to delta ij, delta of t minus t prime. Okay, so this is sort of a fun exercise to do and convince yourself how energy flows between two systems. So with this, the formalism up to technicalities is done. If you've understood everything, you know how to calculate large deviations. You might have to pick up a bit more material, but most of the ideas are here. So what I'm going to do now is I'm going to do some examples, and I'll do them depending on the time that I have. We'll sort of pick as we move along. Questions? This is a great place for stopping for questions.
Hi, Yariv.
Yes.
So in the equation motion, the views do they have some relationship to sigma 1 or sigma 2?
No, sigma. So when the two temperatures are equal, then sigma 1 and sigma 2 are equal. And in that case, you should see that uphill trajectories are exactly the same as downhill.
I mean, the mobility must be related to the diffusivity.
The mobility, set it to be 1. Okay?
Okay.
Right, this is sigma 1, if you want to be strict, is mu times the temperature.
Yes.
Okay?
So then mu for T1 and T2 are different, are they?
No, the same mu. Just set it to be 1. The important thing is that you're
Okay.
coupling to different baths.
And regarding the fixed point, so for the example we had a look, fixed point or happen to be at x hat is equal to 0 line. Is it always the case?
Yes, that has to be, because otherwise you have noise in the system. Okay?
Okay.
And you can see that by inspection directly. I'll again leave it as a small exercise. Just look at the equations of motion, the Hamiltonian equations of motion, and you'll see it immediately.
Okay.
Okay, if you really want, we could look at the Hamiltonian and just differentiate it in your head. Okay?
Yep.
Do it as a small exercise. I trust you.
Okay.
Okay?
Yep.
Okay, other questions?
So in this problem with two different parts, you are saying that the Hamiltonian won't be equal to 0.
The Hamiltonian in the steady state will be 0.
No, for the case where you have two particles driven by two different paths.
No, it will still be 0. No matter, this Hamiltonian equal to 0 is this property. I haven't used anywhere in anything that I've shown you the fact that the system is in equilibrium here.
Okay. Yeah. So what do you want us to do in that problem?
So I'm just going back to the analogy that I was discussing before. The analogy was, if you have a Markov process, you look for values of the Markov matrix, and the steady state corresponds to the eigenvalue 0. So this is what this Hamiltonian corresponds to. So it's sort of a semi-classical limit of that.
Okay. Well, so in that problem, what do you want us to do?
So I want you to do is to convince yourself by looking at histories of creating fluctuations and relaxation that energy flows from the hot bath to the cold bath.
Okay.
Okay, it has to be, right? High temperature, low temperature, the second law guarantees that energy would flow from the hot bath to the cold bath.
Mm-hmm.
If you want to be really ambitious, I haven't done that. You could also verify these fluctuation relations. But I haven't done that. Should be doable, I think.
Okay.
Fluctuation relations for the transfer of heat. 1 over T1 minus 1 over T2 times the heat transfer, e to this. Okay, other questions about the methods, etc., before I jump into applications? Sungan, you promised that you'll be the... okay. Okay, so if this is okay, I want to start with doing some problems, and I'll start. I was asked to discuss some active problems, so I'm going to discuss active escape problems. Okay, so at least I'll do one, and we'll see if and I'll make one point that I think is important for active systems and is not stressed enough. And if we have time, I'll even do another problem on active matter. So what I want to do is so just as for those of you who don't know, active particles are particles with an arrow associated with them, and this arrow drives the particle in the direction of the arrow. So there's some velocity associated with the velocity of the arrow. And then there's some other dynamics which reorient the arrow. So what the particle really does on large length scales is just does diffusion with a time scale that corresponds to with a length scale that corresponds to the velocity divided by the randomization rate. So for example, the rotational diffusion coefficient. So what I want to do is solve an escape problem for a problem like this in one dimension. And what I'm going to do is I'm going to consider a simple model of active particles, which is called the active Ornstein Uhlenbeck particle. And there are other models around. There's a run and tumble particles, and if I have time, I'll discuss them at the end. So specifically, let me define the model. We have a model where the particle is driven by this activity V, but it can also experience an external potential, which is U of X. So the external potential, I'm going to imagine a situation where the external potential looks like this. So we have a minima of the potential at x equals 0, and there's a maxima of the potential of x at x equals s, and the derivative of the potential is here, and the derivative of the is 0 here, and the derivative of the potential is 0 also at the maxima of the potential. And now that I want to give the dynamics of the reorienting particle, and that what we do in the active Ornstein process is, and this goes back to Francesco's question, this is encoded in the dynamics of this velocity through an Ornstein-Uhlenbeck process. What this guy really means is that if you look at the velocity correlation, then it decays exponentially with the time scale tau that is responsible for the relaxation of the velocity. Okay, so what it does is describe the dynamics of particles which have some persistence. If it's moving at velocity v, it's more likely to be moving with a velocity very close to v for a time scale tau, and after a time scale tau, it completely forgets about the initial velocity. And I want to stress that it looks very, very similar to a run and tumble particle, but run and tumble particles have a velocity which is either plus v or minus v, and surprisingly, for some applications, it actually makes a big difference. Okay, so what do we want to calculate? Before that, I want to note that when tau is equal to 0, then v, the velocity, is equal to a white noise, and this is an equilibrium problem. Okay, so I think it's sort of nice because on the way of doing this problem, we're going to solve the Kramer's problem using the methods that we described. Questions?
It's fine.
Yeah. It's fine?
Yep.
Okay.
Hello? Yeah.
Yes.
Very well. So here you have added the potential to the x dot term. Now but unlike usually where we add it to the v dot like in Newton's equation and so on, right?
So when you add it to the v dot, then you're back to an equilibrium problem, right? So what we're doing here in this active Ornstein-Uhlenbeck, which is not just a particle with inertia, we have an overdamped particle, but its velocity has memory. And x dot is not just v, as you're used to. The other problem would be less interesting because it's not active, it's an equilibrium problem. Okay, does that answer your question?
Okay.
Okay, so it's a different model. You could think about V here as an active force that there's a small motor glued to the particle, which is pushing it with a force. And we're actually ignoring the usual noise term that people might put here because it's typically very small in these systems.
But we could add that to the this zeta term you have written, right?
Well, no, you could, if you add it here, it's slightly different, okay?
Okay.
Okay? It's not like adding it here. I'm talking about adding it here.
Okay. Thank you.
So when you turn off the activity, when V goes, when tau goes to 0, just to make this, hammer this in, when tau goes to 0, the equations of motion are x dot is equal to, x dot is equal to minus u prime of x plus square root of 2 zeta of 2. So that's an overdamped particle. Okay, other questions?
There's a question in the chat box.
Yeah, could you please, so tau is the relaxation time of the velocity. So if you take this equation, and I leave it as a small exercise, and you calculate the velocity correlation, then the velocity has a remembers itself over a time scale of order tau. Okay, so after a typical time scale tau, the velocity has taken a completely different value than it did before. And in this case, it's a Gaussian distribution of V. But we won't have to deal with this. Okay, other questions?
So one question. The two Langevin equations that you've written here, isn't the form of equation identical to the Langevin equation for the d-dimensional case that you wrote previously?
Yes, so I'm going to, you have to be slightly, it's a bit, okay, it's epsilon more complicated because one equation doesn't have noise. But yes, you could use everything I've done here because I haven't derived the many degree of freedom case here. I'll just derive it very quickly from 0. Okay? But you're right, it's the same form.
Okay.
Other questions before I start calculating? Okay, so what we want to do is we want to evaluate. So our task is to evaluate probability to cross barrier. So the transition probability. So the probability to cross the barrier, and it's going to take a form of e to the minus phi. Let me check that I've called it phi. Yeah, phi of xs divided by d. So d is going to be our small parameter, and we can self-consistently check at the end, what does it mean that D is small? Okay, you'll see. You'll see as we go along. Okay, so the transition probability, I'm going to use our path integral methods. So we have two, as was pointed out a second ago, we have two variables. So we have to do path integral both over x and over v of e to the minus 1 over d times an action. And I'm going to write the action and explain it. So the action, which is a function of, in principle, of x and v, is an integral over a Lagrangian, which is a function of xv, x dot, and v dot, because we have two variables in our case. And notice that I already put the bounds of the integral from minus infinity to 0. And then our Lagrangian, I'm going to write it in a funny form. Okay, I'll comment about this in a second, is 1/4 of tau v dot plus v squared if v equals to x dot plus u prime of x and 0 otherwise. So let me explain where this comes from. Let me shrink this a bit. V is just a Gaussian process. So if I isolate psi, then I have that psi is equal to tau v dot plus v divided by square root of 2d. If I look at a probability that's proportional to the dt of psi squared over 2, I get that the action that corresponds to this term in the equation is given by this guy. And what this guy is doing is essentially a delta function that enforces a relation between x and v. Okay, so that's all there is to it. If I really wanted, so I'll comment about it, if wanted, could enforce delta function on v equals x dot blah 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 blah, and then you get the Lagrangian, which is a function of x, x dot, and x double dot, which is 1/4 times x dot plus u prime of x plus tau x dot dot plus x dot u prime prime of x squared, where this guy is v and this guy is v dot. Okay, but actually I won't have to deal with this guy. You can deal with it. You only have to be a bit careful when you do functional derivatives, but you can deal with it directly. Okay, so this is the Lagrangian form of the problem. Just because we learned all this Lagrangian, Hamiltonian, let me do the Hamiltonian version also. So we use yeah, sorry.
So in that Lagrangian that you have defined before that,
Yes.
the first one, this should be infinite otherwise, right?
It's infinite otherwise. Yes, thank you very much. Thank you very much. So we don't see it otherwise. Yes, thank you. Careless on my side. Thank you. Okay, so let's do the Martin-Sijaros. So again, we average over noise. And now we have dx, dv, and now we have our delta functions. So this is our first equation of motion and my second equation of motion. And what I want to do is average over all realization of psi. So I use exactly the same trick as before, which is sometimes called statistical physics. I replace the delta function by an exponential form, and that becomes an average over dx, dv, and then we have dpx, dpv, Okay, let me jump a line. Sorry, it's a bit lengthy, but that's life. Minus infinity to 0 of px times x dot minus v plus u prime plus pv times tau v dot plus v minus square root of 2d psi of t. And what we want to do is we want to average this over all realizations of the noise. And when you do this, you find out that you're left with a path integral of the form of dx, dv, dpx, dpv, sorry, that's life, of e to the minus 1 over d times the integral from minus infinity to 0 of px x dot, I'm leaving it as a tiny exercise, minus a Hamiltonian, and the Hamiltonian, which is a function of x, v, px, and pv, is equal to v minus u prime of x times px minus v pv over tau plus pv squared over tau squared. Questions?
Seems fine.
Yeah. It's fine. Okay. So we have our Hamiltonian and Lagrangian path integrals, and the only thing that we have to do now is specify boundary conditions on the trajectories that we're looking for. So let's look at the boundary conditions. You have to be slightly careful here. Boundary conditions. And the boundary conditions are, first of all, I'm going to start at t equals to minus infinity at the metastable state, which I remind you of denoted by 0. Okay? Okay, the other thing is that at t goes to minus infinity, at t goes to minus infinity, remember v is directly related to the noise, so it better be 0. If v is non-zero, then it means that noise is acting in the system, so it better be 0 at time goes to minus infinity, and because the momenta have to be 0 at the fixed point, then we also set the momenta at time goes to minus infinity to 0. Okay, so you can check explicitly that v equals 0 and px and pv goes to 0 are fixed points of the dynamics. Okay, so there's one thing that we're missing, and that's the boundary condition at t equals 0. And the thing with this problem is we have both v and x. So we're solving for trajectories that start here and end here with, in general, some velocity. Now, how do we choose the velocity that arrives at the top here? What would you do? Which one would be the velocity that we would choose?
We couldn't see what you mean by here.
Sorry?
I think your laser point was not working when you're saying here.
So remember, we've set the boundary conditions here, and in principle, I'm going to demand, right? I'm going to demand. Let me just make this clear. I'm going to demand that x of 0 is equal to xs. Okay, but I have to also say something about the final velocity here. So how would you select the final velocity?
I think 0.
Why 0?
Where it is fixed point.
Well, okay, so what you do, you have, so to select, okay, to select velocity at end, have to choose that the velocity that minimizes the action. Okay, so I have to choose dv of S, which S is the action of the trajectory, which is equal to 0. But because dv of S is the momentum at the end of the process, that means that the momentum at the end of the process is 0. Okay? Now let's go back to the action. Because now, is that clear? I have a feeling that I've been a bit too quick. Was that clear? So we have all these solutions, and we could add in principle many solutions. I could fix the final value of V. Okay? But we have to choose the one that gives me the least amount of action, because that's the one that would dominate all the histories. Questions?
So is it leading to non-zero velocity in the end?
It means that, it actually means that the velocity, but x dot is 0. Okay? So your intuition is perfectly fine, but we have to show that.
Oh, okay.
Okay? So now note that the Hamiltonian is equal to 0 at t equals 0. Okay? That we know. So that means that the Hamiltonian is equal, I'm just rewriting it, v minus u prime px minus vpv over tau plus pv squared over tau squared. Now remember, at the end, pv is equal to 0. So this implies that at the end we have v equals to u prime at t equals 0, which is the end of our process. Now remember that x dot is equal to v minus u prime. So Sungan, your intuition is completely correct that x dot is equal to 0, which basically means that the particle doesn't overshoot when it reaches the top. It just comes there with a minimal velocity that it can arrive. Okay?
Okay.
Okay, so your intuition was fine, and you might as well solve this with intuition, but I was trying to be a bit more rigorous. And note that I've used the Hamiltonian formalism for that. Okay, other questions?
Yeah. So if you, can you go up a bit?
Yeah.
Yeah, I mean, okay, yes. So you're basically trying to solve the, let's say, the Hamiltonian equations of motion with the boundary conditions. And so one boundary condition you said was that t minus infinity x is 0, and
Just
also v, px, and pv are 0.
Yeah.
So, right, so then that should completely fix the trajectory, right? So why do you again need, how do you get this freedom to fix the v at time 0?
Vx.
Because if you fix all the 4 initial conditions at time minus infinity, then it should give a unique trajectory, right? So
well, we're starting at the fixed point. Well, you have to be slightly careful. Okay, sorry. You have to be slightly careful. Remember when we solved it, we were doing these limiting procedures. So for example, when we were doing even the harmonic oscillator, let me draw that. So you start at the most probable state with x hat equal to 0 and x equal to 0. But we could find all these solutions that end up at different values of of x hat and x. Okay, so it's really when you do these limiting solutions that you really take care of the fact that you're not over determining this solution. Okay, is that clear?
Okay, yeah.
Because you're right that if you just put, you see, if you just put it as 0 strictly, it never goes anywhere.
Oh, okay, right, yeah.
So we're doing this limiting procedure, and that's why we have this freedom. Okay?
Yeah.
Okay, so even this problem, which looks naively very, very simple, is actually hard to solve. Okay? So for general tau, this is a hard problem. Okay? And I should give credit. So this problem was first considered in the 90s by Ellen Bray and Ellen McKay. And I think Tim Neumann was also on that paper. And you can find, if you want, asking for the reference and I'll find it. Or you could look, we have a recent paper where we sort of extended the results and calculated many things, so you can find the references there, or look at our paper for direct derivations. So what I'm going to do, I'm going to do a perturbative solution in small tau. Okay? So one of the benefits of this guy is that we're going to get, when tau equals to 0, we get the equilibrium. So on the way, we're going to solve the Cramer's problem. Okay, so let me just write down what I mean, and then I'll ask you if you want a break. So the action, which is x of v, actually, is 1. So v is equal to 0. If I really want, no, sorry. I take that back. So xv, so it's 1 over 1/4 of minus infinity to 0 of tau v dot plus v squared dt. And this is subject to the constraint of v equals to x dot plus u prime of x. And what I'm going to do is I'm going to write this as s of 0 plus tau s1 plus tau square s2. So s of 0 is just 1/4 of integral from minus infinity to 0 v squared dt. This guy is 1/2 minus infinity to 0 of v dot v dt. And the last guy is 1/4 minus infinity to 0 of v dot square dt. Okay, so I've just written the different orders in tau of this expression. And one thing to notice is this guy is a full derivative. So it's equal to 1/4 of v of 0 squared. But remember that v of 0 at the end was equal to u prime, because as Sungan pointed out, the velocity at the end is 0. But here we're interested in an escape problem. So this guy is 0 because it's a maxima of the potential. So this guy doesn't play any role in our problem. Okay, so we're left with dealing with this term and this term. And what I'm going to do is I'm going to solve for them perturbatively in tau. Questions? Do you want a break?
Yep.
Yeah, maybe 5 minutes.
Nobody's responding.
Yeah, 5 minutes.
5 minutes. Does that mean that they're all on a long independent break? Okay.
Or if no one wants, I mean, we can do it 2 minutes.
If nobody asks for a break, we'll just go on.
Someone said 5
5
minutes.
minutes.
Yes, somebody says 5 minutes. Yes.
Somebody was brave enough. Okay. Okay, we'll take 5 minutes. If somebody has questions in the meantime, he's welcome to ask them.
Is it true that in higher orders, I mean, wait, I don't see that there are any higher orders in tau, just from looking at this action.
No, because you have to solve the trajectories also perturbatively in tau.
Okay, and in this case, would it be true in higher orders that the odd terms would vanish by the same reasoning?
Yeah, so because we have only tau square, for the escape problem, then there's only even, you know, from what I wrote, you can see that there only tau square can be a perturbative. Will enter, and I'm going to use it. Actually, if you don't do the escape problem and you do the probability at being at a position, the order tau term enters, and it's actually a very, very nasty calculation. You could look at the paper for the details, because there's a boundary layer there, and you have to use a asymptotic matching. But I'm definitely not going to discuss that here. It's a much, much harder problem.
Okay.
But the escape problem is very clean.
And another question, so previously we had for the momentum the interpretation of the noise, but now V is the noise. So do we have an interpretation for the momenta?
Now, for this momenta, PV,
PV and PX.
PX, I don't have a good one for PX. Okay, let me think a second. If I look at the equations of motion, just a second, okay? Let me answer that. The only problem is that. Let me look at Hamilton's equations of motion. I don't have anything clean, no. The equation of motion for Px is Px dot is equal to the second derivative of the potential Px. So no, I don't have for this case, sorry. If you come up with something, let me know.
Okay, and PV does have a
PV
reasonable
acts exactly like the most probable realization of the noise.
And what would be V in this case? If it's not, I mean, if it's not the realization of the noise.
No, PV is the realization of the noise. Right, the momentum corresponds to the realization of the noise. So let me
The
write down.
realization of the noise Xi that you've introduced in the Langevin equation.
Yes.
Okay.
So if I write down the Hamiltonian equations of motion, it's x dot is equal to v minus q of x, v dot is equal to minus v over tau plus 2px over tau, and then we have px dot is equal to u prime prime of px. You see, px doesn't enter the equations of motion for x, so I don't have a clean interpretation.
Okay.
Yariv?
Yeah.
Regarding the fixed points, I think there can be fixed points in the non-zero V hat, although it doesn't seem to contribute to the stationary probability. The location of it is when you have a look at the flow diagram of the Hamiltonian, there's a swirling part, right?
Again, where do you want me to look?
Actually, it is from the yesterday, so there was a x to the the WL potential, and you once wrote the Hamiltonian flow on it.
Yeah.
So and when you have a look at the location between x is equal to 0 and 1, and when x hat is minus, there's a rotating part. And center of that part kind of fixed points.
Yeah, we discussed it yesterday. I don't think these appear in anything.
But it wouldn't contribute to the
No,
stationary property, yeah.
no, because that would cost an infinite action. Okay, just because of the argument that I gave at the beginning of the lecture today.
Yariv,
Yeah,
so you said this h equal to 0 path that correspond to this ground state, right? Lowest eigenvalue 0. So this other path, does it correspond to this? I mean, do they correspond to the higher eigenvalues or?
yeah, you just have the usual Hamilton-Jacobi equations. So if you solve for finite times, you have to look at them.
Okay. But this usually like these eigenvalues are discrete, right? So does it mean that this, but this path is, I mean, like the set of paths is continuous, no?
Yeah, but here we're doing semi-classical approximation. So let me think about that. You could have discrete values, I guess. Yeah, there's no nothing stopping it from happening. I haven't seen too much work on finite time. That's the honest truth. But you're right. Yeah, it could give a discrete spectrum. Yes. I guess I would venture to say that you expect it, because if you look at some confined system, the relaxation time would be finite. So you expect a gap.
So also, is this Hamiltonian method is easier for the, I mean, doing it numerically, because you can get the, I guess, phase trajectories, I mean, numerically, and then, or both are same? I mean, if you want to numerically evaluate the action?
You know, it has this slight advantage. I guess I'm not too much of a big numerical expert, but it has the advantage that they're first order differential equations.
Also, I guess you can directly identify the trajectories, right, in the phase space,
Yes,
which will give.
Yes. I think that, you know, the standard thing for one-dimensional problems is the shooting algorithm. And for more complicated problems, there's all these cloning algorithms, which employ something smarter than this. We had with Guy Bonin at the time, we had a method of minimizing the action directly for field problems by discretizing them.
For which problem?
For macroscopic fluctuation theory.
Okay.
And that worked very, very nicely, actually. We could see singularities in the large deviation functions using it. It worked very nicely. Okay, questions? Should we resume? We don't know if we have to go out, come back. Is this too technical? Do you want me to go through the calculations, or do you want me to, you guys should tell me, or do you want me to stop and tell you results and sort of?
No, I think it's okay.
Yeah. You want something pedagogical?
Yeah. I think it's,
okay.
Yeah.
Okay, so should I continue?
Yeah, I guess.
Okay. So, so as Omer pointed out, there's no, if we look at the escape problem, there's no terms proportional to tau. So if we solve for the trajectory, the most probable trajectory, we have to consider trajectories of the form x0. So this 0 refers to tau, plus tau squared x2 of t in higher order. And similarly, the action will have a term corresponding to phi 0 of xs plus tau squared phi 2 of xs. Okay? So now let's do the zeroth order. Okay? So that we've done. It's zeroth order. Remember, tau equals 0 is equilibrium. Equilibrium, we know downhill is simple enough. It's x0 tilde is equal to minus u prime of x0 tilde of t. So the uphill is just the time reverse. So uphill is x0 tilde is equal to u prime of x0 tilde of t. Okay, that's the solution. So what I'm going to do is I'm going to plug into S0. Okay, which I remind you, this is my S0. So I'm going to plug that solution there. And we're going to do it. It's just a bit of algebra. So S0 is equal to 1/4 integral from minus 0 to tau of v squared dt, which is equal to, okay, everybody has this bug that they write equations and read them out aloud. Squared dt. And now what I do is I take this uphill solution and plug it in here, so I get that the whole thing is just 1/4 times the integral from minus infinity to 0 of 2 u prime of x0 tilde of t, and the whole thing square dt. Okay? So the next thing I'm going to use is remember we have this equation, so that implies that I can write that dt is equal to dx tilde divided by u prime. And I'm not writing the x0 of t tilde. So when I put this Jacobian inside, I get that the whole result is the integral from because I've put in a Jacobian and went from x to 0, from 0 to xs, the position of the maxima of u prime of x. Okay, I can skip this even. Let me write it this way: u prime of y dy, which lo and behold is equal to u of xs minus u of 0, which is what you have to get. So we've done the Kramer's problem on the fly. This means that to 0th order, the transition probability just goes as e to the minus 1 over d times the difference in energies between the maxima and the bottom of the well. Okay, so questions about this? Okay, and again, I've used everything that we've learned to derive this problem. So now I want to take and look at the tau square correction. So I want to look at the tau square correction. So let me look at this action. This is our action. So what we have to do is we have to put in the first correction because of higher orders in tau into S0. And in this term, we can put the 0th order correction because it has a tau squared in front. Okay, so let's do that. And I'm going to do a small cheat. Okay, so let's look at the next order. Okay, so I'm going to look at phi 2 of xs. In phi 2 of xs, I have the contribution from the term that was not proportional to tau, so I called it S0. So I do a variation. So I look at the deviation from the path times the solution that the correction, I remind you, x2 is the correction of order tau squared to the path. Okay, and this is just the derivative, the derivative of the result because I've shifted the path by a small amount. Okay, but now I saved myself a calculation because this guy is maximal, right? This is by definition S0, x0 tilde is maximal at S0, so this guy is 0. So really all I'm left with is evaluating S2 at x0 tilde of t. Okay, so let's do that. So phi 2 of xs is equal to S2 evaluated with the history x tilde of t. Notice that I haven't really solved anything here, right? Minus infinity to 0, and then I have v0 dot squared dt, and this is just, to remind you, this is just this guy in the action. Okay, and all I have to do is plug this v0 dot squared in the solution. So I remind you that, recall that v0 is equal to x0 dot plus u prime of x0. And in the uphill trajectory, this means that it's 2u prime of x0. So v0 dot is equal to 2u prime prime of x0 x dot, but x dot is u prime. So I have 2u prime prime of x0 times u prime of x0. Okay, so all this is algebra. And we get at the end of the day, and there's a punchline coming. The end of the day, I'm going to plug this in and just do the algebra, as Sanjib asks. So I have u prime prime of x, u prime of x0, the whole thing squared dt. I again change variables from dt to dx. And I'm left with the integral from 0 to xs of u prime prime of y squared times u prime of y dy. Okay, so let me copy this and put it in its own equation. So copy, paste. Copy, paste. Okay, so I like this equation a lot. Maybe I have bad taste. And could somebody tell me what's funny about it? Remember this one? The equilibrium one?
Where correction term is non-local function of u.
Sorry?
It is non-local function of the potential.
Yes, exactly. The escape rate in equilibrium only depends on the difference in the potentials. That's quite a striking, when you think about it for a second, it's quite a striking result. If you have a potential that looks like this or like this, really, as long as the difference in energies is exactly the same, the escape rate, at least in the leading order behavior, doesn't depend on any of the details of the potential. And that's one of these robust features of equilibrium that we sort of like to extend without thinking to other problems, in StatMech. But what this shows is that if you go to order tau square, this guy is not a derivative of anything. It really depends on the shape of the potential everywhere along the way. Okay, questions? So can somebody think of a physical effect that would result from this fact?
So can one find the optimal shape for some potential where this guy minimize again?
Well, you could just flatten out it, then it's all optimal.
No, but you still have to maintain the endpoints, right?
Yeah, you could do that. I haven't done that, but yeah, that's a question that one could do, definitely. Yeah, that's something that you could ask. What's the best way?
So another question is, see this transition rate is the expression above. I mean, for a potential which goes to infinity, this is also the stationary distribution, right? The equilibrium distribution.
Yes.
Yeah. So, but this one you have obtained in the weak noise limit, but this is the exact equilibrium distribution. So, is there a way to look at that weak noise is equivalent to infinite time, or is just an accident?
No, here we're doing again, remember we're doing minus infinity to 0.
I know, but this expression is it it's also the exact equilibrium distribution actually, right? E to the power minus beta u. I mean, if the potential at infinity goes to infinity.
Yes.
Right? But this, the derivation was under the weak noise assumption.
Yeah, but it should, you see, the weak noise should agree with the non-weak noise, right? So.
But is it for equilibrium or some non-equilibrium problem? It need not agree, right? Weak noise and the stationary state.
No, for non-equilibrium, well, they have to agree in the right limit. But, you know, if you get rid of the weak noise, then things could change, you know, because then many histories contribute, things change.
Because here, this is for any noise, final expression is true for any temperature, basically, right?
Right, but here, actually, I don't think, there are corrections. There's actually work that, okay, I know that not me, somebody was able to calculate this also without the weak noise assumptions, and there's some extra terms.
Okay.
Okay, and this is also not potential, this is just the calculation that I've done is relatively simple, but only for the escape problem. The steady state probability actually at the given position, even in the weak noise limit, is a very nasty calculation. Okay, but what I was trying to guide you and failed is that one of the things that this implies is ratchets. Because if you take a potential that's really asymmetric, okay, don't know how this came about, just a second. So if you take a potential that's really asymmetric, then it means that if you, okay, that's not very asymmetric. Okay, so if you take a potential that's very asymmetric, then it means that the transition rate to the right and to the left are different, because each of them depends on the whole shape of the potential here. And that implies that you'll have the current generated by an asymmetric potential. So really, you expect this completely generically for all active systems, that the probability distribution would be asymmetric. And in fact, for run and tumble particles, where you can solve them very easily in one dimension, it's very easy to see that the probability distribution is normal. Okay. Question. Yes.
Yeah, just a quick one. Does that I just wanted to have some physical feeling of what we see in that phi 2. The quadratic term, so which is of the second derivative of y, can it be interpreted as some sort of, I don't know, some sort of elasticity, stiffness of some.
I don't have a good explanation. You know, the way, I don't want to be too wordy. The way I think about it, I don't know, is that forces are important. Okay.
Sorry, again, if what?
that in active systems, forces are important.
Okay.
And not only potentials. So
Okay.
U prime is a force, and that's the derivative of the force.
Okay.
Okay, but I don't have a great intuition.
Okay. Thank you.
Sorry.
Thank you.
Okay, so again, the thing I wanted to stress here, and it's completely generic for these active systems, that it's non-local, because this is not the full derivative. Okay, now I want to tell you of some things that can be done. If harmonic potentials can be solved exactly for any time tau. Any tau. And it looks like an equilibrium solution, but with a effective temperature. I don't like any of the words that I'm saying, but they're used all the time. An effective temperature that depends on the spring constant K. So I don't know what a temperature that depends on a spring constant K means, but okay, that's the words that people use. You can also do a lot of progress. So tau goes to infinity limit, can do progress, can do calculations. I'm not going to do them. You can find details of all these things and much more in a paper with Eric Royez and Viviane Lecomte from this year, I think. It just came out. And there's a large overlap with old and beautiful results obtained by Brain and McCain in the 90s. Questions about this? Okay, so now I'm a bit in trouble because I have half an hour and I'm not sure what I want to tell you. So let me okay, let me tell you at least one more story, and then you can ask questions, or I could tell you some other thing if you really want. I want to show something that, so one of the questions that I started with was how different are probability distributions out of equilibrium versus in equilibrium. And I've shown you one example, and the first one that, for example, it's very easy to become a non-local function of the potential. Okay, so that's one take-home message, and actually non-locality appears quite easily in these problems. There's another difference. So first thing, non-local. Okay, what we saw is a function of potential. Okay. There's another feature which I like a lot, and it's the fact that even if equations of motion are smooth, namely, you didn't put any singularity by hand, the large deviation function can be singular. Okay, so it means that the structure of these large deviation functions can be much more complicated than equilibrium ones. Let me just turn on the air conditioner. Sorry, they close the air conditioner a couple times a day, and you have to turn it on again. So I want to illustrate this in a really, really simple problem. So what I'm going to do is I'm going to put a particle on a ring, pull it in a given direction, and imagine that there is some potential Wx on the ring. So the equations of motion are, we're dragging the particle to the right, I guess to the right is here, on a ring, and then it's feeling the external potential W, and then we put in this small noise. Okay, so it's a very, very simple problem, and again, it's just Gaussian noise. And what I'm going to do is I'm going to take the potential W of x to be like this. Okay, sorry. So the potential just has a well somewhere. Okay, so it's periodic, it comes back to itself. So what I can do is that I can define an effective potential. So effective potential for the out of equilibrium problem, which is W of x minus f times x. Okay, at least on one cycle I can do that. So the way this guy looks is W of x as a function of x is just a tilted guy. Okay, so this is the length of the ring that I'm looking at. Okay, so now let's think in terms of what we've learned about the equilibrium problem. The equilibrium problem, we start at the most probable state, we calculate the uphill trajectory, and this is an equilibrium problem. It's going to be a smooth function. It's going to be e to the minus the energy difference, and it's going to be look like a very, very nice function. Now, what I want to do is I want to look at the case where I have my non-equilibrium problem. And I leave it to you as an, if you want, as an exercise to solve it using the method I showed you with two fixed points of the solution. Specifically, the fixed points are here and here. This one is equivalent to this one. But I want to argue heuristically for the steady state probability distribution here. So remember, we're looking for the fluctuation that costs the least amount of action. So we start from this minimal position. And if we look at a position close to here, then it's clear that the history is going to look like this. If I look at the position here, it's clear that the history is going to look like this. And obviously, locally, it looks like an equilibrium problem. So we can even tell that it will look like e to the minus, so the large deviation function locally will look like this. Okay, we'll take this exact shape. Now let's climb higher. What about this point? Okay, so let me mark it in red. Okay. What about this point? What's the most probable history of reaching it from here? Can somebody tell me?
On the right?
Yeah. So the most probable history of reaching this point is climbing up to the right and then sliding down. Remember, sliding down, no cost at all. Okay? Exactly the same is true for another point that's sitting here. The most probable path is going to be climb to the right, slide down here. So if I look at the steady state probability distribution, even in this very, very simple case, you know, almost the simplest non-equilibrium problem, almost the simplest non-equilibrium problem that you could think of, then what happens is that all the points which are larger than this baseline, all the points here will be reached by climbing to the right and just sliding down. So if I plot the large deviation function, phi is a function of x, its shape will be like this. It will be completely flat here with a singularity here. Okay, and that's a very, very generic feature of large deviation functions, and it occurs even in more complicated systems with more degrees of freedom, and even in simple diffusive fields, which are driven out of equilibrium. Then the probability distribution of the density by a very, very similar mechanism. You see, the mechanism, if I want to summarize the mechanism, is that to reach this point, there's two possible histories that I can solve. One is going to the right, and the other is going to the left. And when I shift this point towards this singular point, then at the singular point, it suddenly becomes more probable to use this one than to use this one. So this is a completely generic feature of many non-equilibrium systems, that when you calculate the large deviation functions, when you look at your final configuration, suddenly you find out that instead of having one history that leads you to this final configuration, suddenly it's much more productive, meaning that I use lower action to reach the configuration using a completely different path. And that generically leads to a singular behavior in these large deviation functions. And for some classes of the system, now we understand pretty clearly when do we have such singularities and why do we have them. Questions about this? Who's brave enough to say, I didn't understand the single thing that you said? Please repeat everything. You were not, somebody, I won't be offended if somebody tells me you were completely unclear. Please repeat this again. Questions?
So is there a 1D system, like this one is a periodic ring, right?
Yes.
But can you have on a full line in
No,
some force?
No, because one-dimensional systems, you can unless they're on a ring, you can always write an effective potential.
Yeah, that's true. Actually.
So you can't have that. But in 2 dimensions, it's very, very easy to get these singularities. And there are very simple models with 2 degrees of freedom that have been done that. And remarkably, in the 80s papers by Graham and Tell, they even have some experiments which show this on oscillators, macroscopic driven oscillators. Mm-hmm. These things have also been observed experimentally. Mm-hmm. And it's again, this really the idea is that, you know, if you have in this case, it's periodic boundary conditions, it's general for other systems, it's nonlinearities. And once you have nonlinearities, nothing prevents multiple solutions. And it's true that generically one wins, but as you move in your configuration space, then many times you jump from one configuration to the other.
So this one, it basically means that this the place where the large deviation function is flat, so probably the scaling is different, right? P of x will go like n to the power some other powers, probably, right?
Yeah, so there's corrections, higher order corrections, which if you want, you can calculate. Okay. Yes.
And do you know, like, how does it behave? Like, what is the large division form, not in exponential of minus n, but in some other?
I know there's one case that I know that is the problem that I talked about before, the Ornstein Uhlenbeck. It also has a singular part like that. And if I remember correctly, we've worked it out, but also actually also Bray sort of heuristically argued for it. I think it's the 1 over, so it still goes with 1 over, okay, it's slightly different. Okay, no, I don't know the answer. Mm-hmm. I think it's out there, but I don't know the answer, mm-hmm. Okay? Sorry. Other questions? I don't think it's very hard to work out, actually. For this problem, definitely. Other questions? So I have 18 minutes. You could just use it to ask questions, which doesn't look like promising. I could describe very, very quickly the Cramer's problem for run and tumble particles. I don't think macroscopic fluctuation theory, I'm not going to do in 18 minutes. I could show you in 2 minutes, maybe that would be the preferable thing for people. I could show you a movie of run and tumble particles escaping from a well and explain briefly what happens. Sanjib, Abhishek, do you have any preference?
We run and tumble.
Run and tumble. Okay, so I'll explain it very, very quickly, okay? So escape, run and tumble. Tumble, and you could do this in any dimension. Actually, I'm going to discuss the one-dimensional case here, and this was done in a paper with Eric Royez, Yongfeng Zhang, Viviane Lecomte, and Julian Taillot from last year. Okay, so I'm going to consider the following problem. We have, again, a particle subject to a potential. We have this activity. And now, instead of V being a Gaussian variable with a memory, we have U, which takes the value plus or minus 1, and it flips between them with rate alpha over 2. And then, if we want to do a Cramer's problem, then we better add some small noise. So the question is, how does this particle escape from a potential? Okay, so there's some barrier, and you want to escape from this potential outside. So because we don't have too much time, I'll just do a heuristic argument, and then I'll do something which I think is neat at the end. So the first thing to note about this, it's true the noise here is small, but because we have this activity, we have a force that's driving the particles. As long as the force exerted by the potential is smaller than V, then we don't have to use the noise to reach these points. It's actually, even if this guy is 0, I can reach every point where the force exerted by the potential is smaller than V. So what I'm going to do is I'm going to mark these points on this graph. So on this graph, I have these points C1, C2, and we might as well do C3. And everywhere here, the particles move freely. It's not a rare event. Everywhere here, the particle moves freely. It's not a rare event. But in this region, I have to use noise to cross it. Okay? So I could do the calculation fully. Let me write even the Lagrangian, because hopefully we're accustomed to dealing with these Lagrangians by now. So the Lagrangian is equal to 1 over 4 times x dot plus mu dxv minus v times u square. And I have to take on that, add randomness in u. Okay, so let me be more explicit about what I mean by this, is that the transition probability, what I have
are C1,
sorry?
C1, C2, and C1, C2, C3 are the points where force due to activity and the potential balance each other.
Yes, exactly. Thank you for making me stress it. This is the point where this happens, okay? Because reaching these points is easy. So the transition probability, what I have to do is I have to go over all histories of x. If I write down the path integrals, all histories of u, e to the minus 1 over d times the integral from minus infinity to 0 of the Lagrangian. And then I have the probability distribution of the u, which I have to account for. Now, we could, what I want to argue now is that actually I don't have to worry about this thing. Now, let's think about this. These are particles which are biased and flipped to the right and to the left. Now, this instanton, this trajectory that goes from here to here, is the one that minimizes the action. What sort of history over u will minimize the action? Does somebody have an idea?
Just a constant direction.
Yeah. The only guys that will survive are the guys that are always pointing to the right. Because if I flip the direction again and again, then I climb up, go down, have to climb up again, go down again, climb up again. So really the instanton has only the guys that are moving to the right. Okay? So only guys moving to the right means that I have to only deal, and again I'm being a bit quick, with the Lagrangian, which is 1/4 of x dot minus mu dxv minus v squared. Now this corresponds just to a tilted potential, v of x minus v over mu x. So we have an equilibrium problem with a tilted potential, which we know how to solve. So I can write down immediately the large deviation function, and it's given by mu, the difference in the potential in 0.2 minus 0.1. But we have also this tilt guy, which is C2 minus C1. Okay, so this is you see, much simpler than the previous problem in some sense. This is the Kramer's problem for active run and tumble particles. Now comes the neat part. The thing is, remember, C1 and C2 are the points where the active particles are stopped by the potential. Okay? So C1 and C2 are functions of V. So what I'm going to do now, I'm going to think about what happens when I look at the escape rate as a function of V.
Yariv,
Yes.
But I mean, this constant velocity, if you put u hat equals to constant, but that comes with a huge, like it's exponentially like less probability, right?
Only if alpha is very, very small.
Sorry, what was alpha?
Rate is very, very small. And we're looking now at the limit where the D is much, much smaller. Okay, so D is the slowest process in the problem, in what I'm looking at.
So the flip, you're assuming that the flipping rate is
finite.
Yeah, but then it would flip, like if you're looking at a large time, it would flip many times, right?
But still the instanton is the one with the lowest action. And the lowest action is it doesn't flip. Unless you take a funny limit where you're making the cost of alpha be so large that it starts to cost more than climbing up the hill.
Okay, so because, I mean, like basically, wouldn't it, if you go down a bit, yeah, so in the path probability, wouldn't it come in the P of U would be very small, right?
Yes, so if you take a limit where that's the dominating guy, then I agree with you.
Okay, so you're working in some limit where somehow that...
where flipping is not the big issue, which is the typical case in these systems. Okay? It's not the hard thing to do. So there's a question
in the chat box also.
Sorry?
There's a question in the chat box also.
Yes. So the RTP and Brownian particle with constant drive would have the same transition rate? Yes. Completely correct. but I'm going to show that it's sort of neater than this in the 8 minutes that I have, or if you give me a bit more. So this equation, let me rewrite it, but now emphasize that it's a function of V. So we have mu V of C2, which is a function of V, minus V, which is C1, which is a function of V again, and minus V, C2 of V, minus C1 of V. Okay? Now we know that at V equals 0, we have Kramers. So we have mu of V of C2 minus V of C1, where now they're the top and bottom of potential. Okay, so that's the Kramers thing. Now, note that if I, just a second, can I explain this in a simpler way? Sorry, because I'm a bit short in time, I'm trying to think. Yeah, okay, yeah, this is simple enough. That if I, let me see if I can skip this and make it shorter. Okay, let me skip one step. Again, if you want more details, I'll do it. I'm just trying to save myself a bit of time. It's not too hard, but I'm going to save time to show that phi prime of V is equal to minus C2 minus C1, which means that it's a monotonically decreasing function. And also, what you can also show, and that's sort of obvious, that there's a critical value of the velocity, which is given by the maximal of the force exerted by the potential, where beyond this point, we have that phi is 0. Because if the force is, if the velocity is so large that it can overcome any of the forces exerted by the potential, then you could just slide over this potential without any cost. Now let's look at this equation. Specifically, these equations, specifically, this equation means that the slope at V equals 0 is equal to the difference between the maxima and minima of the potential. So let me draw phi as a function, phi of V as a function of V. Okay, so what I can do, I look at the slope of this curve using this equation. I look at the slope of this curve, and the slope locally here is dictated by the difference. If I have my potential that I'm escaping, then it's given by this length. Okay, so I have a curve that looks like this, and then there's some V, which is V critical, which is where this large deviation function goes to 0. Now recall, this slope is dictated by the width of the potential. Okay, so what I can do is I can take a particle, and again, I'm being slightly quick. I can take a particle which is sitting in a really asymmetric potential, one which is very wide but has a steep part, and there's another part which is narrow but has no steep parts. Okay, so this is supposed to be narrow. Sorry, I'm a bit in a rush, so I'm not doing it in the best way. And this is supposed to be wide. Okay, so if I take a potential that's wider than this one, then its slope is going to start here. So let me do it in red. So this is wider potential. But if it has a very steep part, then you can have that V critical of this guy is larger than the V critical of this guy. So if I extrapolate, what I find is that if, as a function of the velocity, I can move between crossing one potential or the other. And this is, again, this manifestation of the fact that you really care about the whole shape of the potential and not only on the difference in the potential. And you could also do it, and you could actually use this idea to design a system such that you start with a system with a low barrier and a high barrier, and low velocity particles will cross over the low barrier, but high velocity particles will preferably cross over the higher barrier. So you could do all these funny games with these systems. Okay, there's a question. There will be a wait. Alpha t. Yes, so again, this e to the minus alpha t is a subdominant contribution to the action. You can actually, and we worked out in the paper, it's a very unpleasant calculation, a very long calculation. You could also work out, so the general form of the equation is e to the minus n phi, and there's a prefactor sitting here, and the prefactor has actually inside of it e to the minus alpha t times the time of the instanton. So that, as long as alpha is not, doesn't make this the dominating process, then the physics that I've discussed is the relevant one. So I hope it answers Ayon's question. Questions?
Regarding the singularity problem we saw from the periodic case.
Yeah.
So what will happen if you have to get the current going through this potential? What will be the manifestation of this?
Well, you'll have a current. The fact that it's out of, so you can see that immediately once you're out of equilibrium, the singularity will occur, and you'll have a current that for these weak noise problems, this current will go like e to the minus n times the price of crossing this guy. Okay? So in this case, it's just the difference in potentials. Okay, because you can calculate the current as the probability of going to the right minus the probability of going to the left. Because we're in the large deviation regime, the going to the left can be neglected.
Sure, yes.
Okay. Other questions? Sorry, I have a feeling that I was way too quick, but I'm happy to go through things slower if you want me to clarify things.
So are there experimental studies on the escape problem for active particles?
No, not that I'm aware of, not so far. I've heard of somebody wanting to do something, but I don't know if they actually did it. I think Corona started quite quickly after that.
And also, like in the case of RTP, just naively from the expressions, it appears that the rate function doesn't depend on the shape of the potential, just at the endpoints.
In this case, but again, there's this subtle dependence, which, okay, I haven't emphasized enough, which is sitting in the values of C1 and C2. The values of C1 and C2 are very, very specific to the potential. Which is what caused this transition between these two behaviors.
Okay,
so it's not in the expression explicitly, but it's definitely hiding there.
Okay.
references for AUPs and RTPs. So, you know, just go to ConMet and look up my name. I have the AUPS is a JSTAT MEC, but in the archive, it's 1912. And I suggest that you also look at the references inside because there was lots of work done before us. For the RTP, it's a paper with Eric Royez and colleagues, which is a PRL from 2019. Okay? Other questions?
Yeah, so Yari, for if we are let's say looking at the RTP in a harmonic well, then of course one has a steady state which is known exactly.
Yes.
If we do this way, I mean, can one sort of approximately get in some series form or the
Similar to what you guys were doing.
Yes, so this you can do exactly, but I'm saying, can you do this in a perturbative way or some way using this approach?
In one dimension?
Yeah.
With a small d.
Right, yeah.
Yes, yes. I think that's, you can get it from, yeah, I think as long as, yeah, I think that's definitely doable, yes, using this approach. Yes.
Okay, so it should be some series thing which should, maybe it will give the
yeah,
exact result.
with a finite, so I'm just making sure I understand you. So RTP is in one dimension with a finite d. The solution is not known, and one could.
Sorry, say again.
RTP is in one dimension with a finite diffusion coefficient. The solution is not known, as far as I know.
So okay, yeah. Without diffusion, it's known. With diffusion, I guess it's not known, right?
It's not known, and one could use this approach. Yes.
Okay, but if you take this, okay, and then it might be difficult to take the d going to zero limit and.
You know, it's higher order as in saddle points. I don't know. Maybe for this, you see, I haven't. It's a good question. I haven't attempted it. Maybe it's doable because the instantons here are pretty simple.
All right. Yeah. Okay.
What I can tell you. Okay. What I can tell you is that I'm not so confident anymore. Because what I can tell you is that we worked hard on this coefficient, which is is a correction to the saddle point solution. So at the leading order in 1 over d, you could do it. Sorry, this should be 1 over d. The coefficient here is the most horrible expression that you could imagine. It's literally okay. You know, it has gamma functions, and you have to take finite parts of integrations. So I take it back. I think maybe to leading order in D you could do it, but getting the series expansion I think might be a nightmare.
Okay.
And it was a really, really difficult calculation doing it. Other questions? Okay, so there's tons of other works on large deviations, which I haven't covered. Large deviations of current, of density distributions, etc. But I hope that if you followed me, and if I did a decent job, at least you can pick up papers and understand the main ideas and methods that are used. So thank you very much for your time.